to like what is U substitution and what is this process of U substitution. I like looking at examples of ones that we would do with U substitution, but ones that we can also kind of do mentally. Because U substitution is a process, but we don't have to do it every time. I'm losing my pen. There we go. So where U substitution comes from is it's kind of like undoing the chain rule. For example, if I know the derivative, if I'm looking for, the derivative of the sine of 3x, what is the derivative of sine of 3x? Cosine of 3x, not the highlighter, cosine of 3x times what? 3. So we know that when we're doing the antiderivative, we're going backwards. Well, the problem is not going to be usually written with that 3 written in the back. That's how we wrote it when we did the chain rule. The integration problem might be written as 3 times the cosine of 3x. And we'd have to kind of just mentally know, where did that 3 come from? It came from the chain rule when we did the derivative. So when I integrate 3 cosine of 3x, that is going to give you sine of 3x plus c. So we're going to kind of think about how we are undoing the chain rule, which is a little bit weird. Same thing, we learned how to take the derivative. If I say what's the derivative of 2 plus tangent of x to the 9th, we know that 9 is going to come down in front. The n side is going to remain the same. The new exponent is an 8 times the derivative of the n side. If you're just looking for an integral, often the integral won't be written that nicely, so you can kind of clearly see the chain rule. The integral will often be written something like this, like 9 secant squared of x times that 2 plus tangent x to the 8th. And we just need to get used to kind of recognizing, like, where would that 9 have come from when we took the derivative? Where would that secant squared have come from when we took the derivative? And how do we undo that? Since that's always not easy to see, there are going to be some examples we look at today where we just can kind of look at it and imagine what undoing the chain rule will look like. But then there are going to be other problems where we want to have like a set process of how we do U sub. Alex?
Can I get a
battery? Yeah. So the next example I want to look at is ones where we talk about what is this thing called U sub, when will we need it, and when would we not need it. So looking at those examples, similar to when we first did the derivative and chain rule, we talked about like when do we need the chain rule and when do we not need the chain rule. In general, we're going to use this thing called U sub when we have like something raised to a power, but that's not always true. That's going to be kind of a little bit different because some rules we know have powers built into them. For example, this first column are all ones where we do not need to do U substitution. Like 4x to the 5th, we know immediately what is the antiderivative of that, but 4 6x to the 6th plus c, and of course you could reduce that to 2/3. A similar to one where U sub makes it a little bit nicer is we have this 4x plus 2 to the 5th, so that would be one where we need to do U sub. Same thing with trig. We know the integral of sine. That would be not a U sub question. The integral of sine is negative cosine plus c. We know the derivative of negative cosine is going to give you positive sine. Where U sub is going to be more important is where we have this integral of sine cubed plus cosine. And you can kind of see how a U sub is going to allow us to undo the chain rule. Like we have something raised to a power, and I see that the derivative of sine, the derivative of the n side is also in the integral. So you can kind of see that would be like an answer you got if you did the chain rule. We have to undo that in order to find the antiderivative or the integral. And then this last row is one where students I often see make mistakes. That very last one, we see secant squared of x. And you're used to, like, if you just think about the chain rule, you're like, oh, I see something raised to a power, taking the derivative as the chain rule. And it's not necessarily true for the integral. Like, yes, secant is inside the squared, but we know what the integral of secant squared is, because the integral of secant squared is tangent of x and then plus the c. So we will have to be careful because we can't really just say in general, when you see something raised to a power, you do U sub like we can for chain rule. We do have to keep reminding ourselves that some integrals have like powers in them. This would be one where we have to do U sub because we have something inside of like the secant squared. So we would have to figure out a way to undo that when we find the antiderivative. So before I show you the longer process, I'm going to give you, I think I have 3 examples. And these are 3 examples that I think that you can do pretty mentally. So like have this analogy, like you looked at analogies probably like in elementary school, but like just think about it like U substitution is to integration as the chain rule is to differentiation. If you think about the chain rule, you basically have to think through backwards, like how do you cancel out, like where you multiply by the derivative inside, and how do you figure out what that new exponent is going to be. So 3 examples. Go ahead and try these before I show you the longer way to do it. These will be 3 examples where I would not expect you to do any long process. I think everyone in here can basically figure these out kind of just mentally. And how I have it set up to check your the black typed out the integral that I want you to find. And then we know that when we find an antiderivative, we can easily check our answer by just taking the derivative of it. So go ahead and try those 3. Again, these are what I would consider like mental U-sub problems because you can easily kind of figure out like what coefficients might need to be in order for that antiderivative to work. But go ahead and try those 3, and then we'll look at ones where they aren't so easy to do mentally. And again, you can always check your antiderivative because this derivative should give you what you start with. So looking at that first one, you have the integral of x squared plus 5 to the 7th times 2x. Some things just to be clear about, like with integrals, you can't just integrate each factor. It doesn't work that way. There's no product over integrals, so we do need to do U sub. The derivative of what is going to give you what you see in the integrator? If someone wants to take a guess at that. Or what would have been like the initial coefficient. We'll start there. 1/8. So we see that something canceled out. 1/8. We know the inside stayed the same. New exponent was the 8th. Don't forget the plus c. And I would agree that's the answer because we can check it because what is the derivative of 1/8 x squared plus 5 to the 8th? That 8 comes down in front, canceling with the 1/8, so the coefficient goes to 1. New exponent is the 7th, and then times the derivative of the inside, which is 2x. So that one does check out. Looking at that second one, what would be the integral of the square root of tangent of x times secant squared of x? Any ideas there? Go ahead, Matthew.
2 over 3 tan x to 3 over 2 plus c.
I agree with that. So again, you can check yourself. So like that 2/3 in the front is going to be canceled out by the 3/2 when you take it down. When you do the derivative, 3/2 minus 1 is going to give you 1/2, and that's where the square root is coming from. And of course, that plus c is going to go to 0. What about that last one? If I integrate secant of 4x tangent of 4x, think to yourself, the derivative of something is secant 4x tangent 4x times 4, excuse me. What would be your antiderivative for that one? Go ahead again, Matthew. Not tangent of 4x, secant of 4x, yeah. Plus c. And we know that works out because the derivative of secant is the product of secant times tangent times the derivative of the inside, so times 4. So those are ones that we can do, I think, mentally. I think some people still want to have a reliable method that works every time. And that's kind of where this process of U substitution comes into play. And I do want to emphasize kind of like the chain rule. The chain rule is not really a formula, it's more of a process. U substitution, even more so, is not really a formula, but a process. So when we are doing U substitution, there's this kind of big idea that we want to look at. And the big idea comes from a way that we can rewrite what U prime is. So it's called U substitution because we are basically substituting in a U. And what that U often represents is like the inside of something. So in calculus, U prime we know is the derivative of U basically. What's another way we can write U prime using a different notation? The Leibniz notation. How can we write that in the Leibniz notation? Du over dx. So this means the same thing. We know that U prime is equal to du over dx. Those are just two ways of saying the same thing. And I know normally we don't split up that fraction du and dx, like often we look at that as a single symbol, but we can split up, those are individually called the differentials. If I multiply by dx on both sides, we get this new statement of U prime times dx is equal to du. And that's really the idea that's happening that allows us to work backwards. You may not have thought about it that way, but that's what your brain was doing when you're doing those mentally. Not going to do it for all the ones we just did, but kind of see how that lines up. So we already did this one mentally, but if you rewrite it, so I have the integral, U often represents the inside, so you can think of that as U to the 7th. The 2x is the derivative of the inside, that's U prime. And then you have a dx at the end. Well, we just saw what is U prime times dx. U prime times dx is the same thing as du. So basically the idea behind U substitution is instead of always having to do it mentally, we're going to take our integrals that are often like with respect to x or with respect to t or with respect to theta and putting it with respect to u, which then makes it a much easier integral to find. That becomes 1/8 u to the 8th plus c. Well, what was u? U was that x squared plus 5. So it's going to allow us to take these integrals, make them simple so that we can integrate them easily, and then put it all back in terms of x or whatever the variable is. And that's also why, notation-wise, we always want to have like a d something at the end of an integral sign. Like those always go together. Rewriting the second one, I don't really worry about that third one. We can kind of see that process still works. So I see that tangent's basically what's on the inside of this one. Secant is the derivative of the inside, and that dx is still there. That becomes u to the 1/2. U prime times dx is the same thing as du, and then that becomes a much easier thing to integrate. You don't have to worry about trying to figure out what cancels. You end up with u to the 3/2. 1/3/2 is 2/3 plus c. And then what was u? U was the tangent of x. So that's basically the idea that we're going to be doing when we are looking at these problems. One of the trickiest parts when you're starting off with these problems, sometimes it's easy and sometimes it's difficult to choose the correct u. Sometimes it is just going to be directly what you see inside of an exponent or inside of a power or inside of a function. Other times it can be a little bit more complicated. So, steps on how to choose u. When I'm looking to choose u, I kind of think about really two main things. The first thing I want to do is I want to choose a u so that its derivative or a constant multiple of its derivative appears elsewhere in the integrand. And of course, we are going to call its derivative basically u prime for notation-wise. The other thing I'd like to consider is simpler is often better. And I did kind of choose that word choice on purpose U isn't always going to be the simplest thing in the function. Like we'll see that depending on a lot of these, sometimes U has to be more complicated for it to work out nicely. And then the last step is going to be just more of like a very teachery thing to me to say, and that's just going to be to practice. And the reason why I think practice is important is because you have to think you are undoing the chain rule. And you think back to when you do derivatives, like you can find the chain rule and then you can simplify that problem. Like sometimes you have to get like a common denominator to simplify it, sometimes coefficients canceled out, sometimes variables canceled out. And it's a lot harder to go in reverse in math, and you just want to be exposed to a lot of different problems to kind of see how picking U kind of works. Sometimes it's easy, but there are definitely examples where choosing the correct U can be a little bit more difficult. So for the first example that we look at, so I can kind of show you the full process, I'm going to start with an indefinite interval. We'll be looking at U substitution for both indefinite and definite intervals. And so I want us to integrate cosecant squared of x all over cotangent cubed of x. So things to kind of point out, like we don't have a quotient rule for integrals, so I can't do anything like that. This is trig, so like you could maybe spend some time trying to rewrite this one using trig identities. When I see this one, I know it's going to be U substitution, and I hope with practice you can kind of see that it will be U substitution as well. The reason why I know it's U substitution is because I can look at this. There are two things inside an exponent, but the derivative of one of those insides is elsewhere in the problem. And what I mean by that is we want to find a U. We want to find the inside kind of something so that U prime is going to be somewhere else in that problem. You have lots of different options for U, like you could let cosecant squared be U, you could let cotangent cubed be U, you could let cosecant be U, or you could let cotangent of x be U. Some of those are very, very bad choices for U, and some of them are, well, one of them is the correct one. Which one would be the best choice to pick for your U variable? Cotangent. Oftentimes we'll look in the denominator, but we can kind of easily check it. So if I let U be cotangent, the derivative of cotangent is going to give you what? Negative cosecant squared. And so we can easily check that this works. Is a constant multiple of U prime somewhere else in the problem? Yes, so like U prime was negative cosecant squared. I see a cosecant squared in the problem. That is a good thing that you want to see. An example of a case where something bad would be happening, say you let U be, so this would be wrong. You wanted U to be the cosecant of x because you see that that is inside the problem. U prime would be negative cosecant of x cotangent of x. This U prime doesn't have a constant multiple that's like elsewhere in the problem. Like there's some more stuff left over. It's just not going to work out nicely for you. So that's where you want to get kind of practice with choosing the correct U. You want U prime to be somewhere else in the problem. And then we have the big idea. U prime, just to remind ourselves, another way to write that is du dx, the derivative of U with respect to x. Multiplying both sides by dx, you get U prime dx is equal to du. And I'm going to rewrite that one more way. So if we say U prime is equal to du over dx, multiplying both sides by dx, we get that next statement. Dividing by U prime, we get du over U prime. And if you want to memorize anything, I'd probably memorize that last statement. It's important to know where it comes from, but at the same time, I think it's like that's what we're going to end up using. So yes, U prime is the same thing as du over dx. Just doing some simple algebra, that's the same thing as saying dx is equal to du over U prime. And why is that necessary? So this is called U substitution. So we're literally going to substitute in a whole bunch of things to put it into terms of U. So here was my original problem. Doing my substitution, so I have the integral. Instead of writing cotangent cubed in the denominator, I said U was cotangent, so this becomes U cubed. I'm going to leave that cosecant squared of x alone in the numerator right now. And then we just said that dx is the same thing as du over U prime. So dx, I'm replacing with du over U prime. So I literally did my substitution, and then I want to simplify it. Now, for this to work out correctly, you want pretty much all the x's to cancel, and you want what was an integral with respect to x to become an integral with respect to u. So if I'm looking at this one, the cosecants cancel. Don't forget that negative. So if I'm simplifying this, I have an integral sign, a negative on the outside, 1 over u cubed with respect to u. So instead of having a complicated integral, I now have an integral that's much more simple, and then that becomes a pretty easy one to evaluate. So I have the negative. This is the same thing as saying u to the negative third, and then I can go ahead and integrate it from there using the power rule. So that negative 1 is going to carry across, add 1 to the exponent, divide by the new exponent, gives me a 1/2 in front. Don't forget your plus c. That will be the antiderivative of your with respect to u integral. To make it the correct integral, you're going to plug what u was equal to back into the problem. And what was u equal to? The cotangent of x, which we could simplify as 1 over 2 cotangent squared of x plus c. So that's the basic process of u sub. You can do certain parts in your head, like with practice. I think many of you will be able to find u prime yourself and kind of jump straight to certain steps. You don't have to show your work with u prime, actually with u substitution. I would just say, if you want partial credit and think you might make mistakes, then definitely still show your steps. Matthew.
Where did u came from?
That came from, so I had cotangent cubed of x, and I just said u was cotangent of x. So if I plug in u for cotangent of x, it becomes u cubed. And that's basically the idea. This is also why when you're choosing a u, you want u prime to be somewhere else in the problem, or at least a constant multiple left over. I didn't really want to have any x's left over. I wanted all the x's to cancel, so that it would then be in terms of u. Any other questions on that one? All right, so I reordered it because I wanted to try some examples before I do the definite integral. So if you're in OneNote, look for the slide I titled Try These. And then try them yourself. So these are 2 indefinite integrals, and I want you to evaluate them using u substitution. Again, some of you might be able to look at this and do it all mentally, which is great. That's allowed. If you follow that process of u substitution, then you're pretty much guaranteed not to make a mistake. But of course, if you ever want to check your answer, take the derivative of your antiderivative, and you should end up with the original integrand in the problem. But take a few moments to try those, and then we will move to the definite integral, which does complicate a few things when you're doing it with yourself. I'll give you a moment to try those before I just jump in and do it. And as a general rule, you are going to be choosing a u that's inside of a power. But I don't want to say that it's always going to happen, and we'll see in cases this week where you don't always let u be what's inside of an exponent. shows the correct u when either u prime is exactly in the problem or a constant multiple of u prime in the problem. Yeah. Yeah, 3 times 3 is definitely 9. Yes. Yeah, that's I do things correctly. Thanks. So there's my work for both those. I want to check with yours. Again, I want to keep emphasizing like why we can do this, and the reason why we can do this is because if u prime is the same thing as du over dx, doing algebra, dx is the same thing as du over u prime. So again, we want to choose an inside who has its derivative or constant multiple of its derivative elsewhere. So in that first one, if I let u be 1 minus 2x squared, u prime becomes negative 4x. So doing my substitution, dx is du over u prime, and then we have x over u squared. The x's cancel, which is ultimately what we want. There would be a negative 1/4 coefficient that we need to worry about, and 1 over u squared, the same thing as u to the negative 2. Then we just want to find the antiderivative. Coefficients carry straight across. Add 1 to the exponent, divide by the new exponent. We end up with 1/4 u to the negative first. And I just put that back in the denominator, making sure I plugged in u into my final answer and not leaving it in terms of u, but back in terms of x. Same thing for the second one, but we left with a 1/3 on the outside, and then find the antiderivative, bringing across the coefficients, and then plugging back in what u is, having in terms of x, because both of these are indefinite integrals, we would have to have plus c at the end of our answer. Questions on indefinite integrals before we start doing definite integrals and u substitution? All right, so with definite integrals, so if you're following along, you're probably going to jump back up. There's 2 ways to do definite integrals with u substitution. I definitely have my preferred method. You do need to know both of them for the AP exam because they have a way of asking multiple choice questions that will be like, which of the following will be like the first step of u sub, and you have to be able to match up like an equal answer. For me, the easiest way to do a definite integral when you have to do u sub is to just treat it like an indefinite integral, work it out like an indefinite integral, and then at the very, very end, plugging in like the top number minus the bottom number. There are some things we have to be careful with. The AP exam, and so I am as well very, very picky about the notation you use, I should say. When you start doing U substitution, like you're saying that you are turning in that integral to be in terms of U, so those numbers on that integral sign are no longer valid. And I'll show you what I mean by that when we work out the example, and I'll definitely show you things that you don't want to do. But the first thing you want to do is, like, when I see an indefinite integral, I just pretend that it is simply an indefinite one and work it out like it's an indefinite one. So go ahead and try that one for me. Ignore the numbers. And again, as you work it out, just leave the numbers off the integral sign, or you will run into some notation errors. So just treat that like an indefinite integral, and go ahead and find that integral using U substitution for me. And then we'll basically evaluate it from there. So here's my work, and I'll kind of explain my reasoning, and also show you what you definitely don't want to do. Not that you would get the wrong answer, but you would lose points on your notation. So first step is just pretend that it's an indefinite integral. For the AP exam, I would recommend writing down the indefinite integral that you're evaluating. Go ahead and do your U substitution. One thing where you would lose points on is if you wrote down your integral and you had it in terms of U, and you put numbers on it. You would automatically lose points if that was on your paper. The reason why you would lose points if that was on your paper is because when you say du, that means you are in terms of U. You're taking the integral with respect to U, so you should be in terms of U, but these numbers are in terms of which variable? X's, so those are in terms of X. So that would be considered poor notation, because you're mixing together like X variables with U variables. So as soon as you write that down, you're going to have points taken off. So I just recommend treat it like an indefinite integral, work it all the way down like an indefinite integral with the plus C, and then just kind of in a separate line, notice I never went back to the integral sign. Once I had that antiderivative, we know the definite integral tells you to plug in the top number minus plugging in the bottom number. So you can simplify that number or leave it exactly as it is. So treat it like an indefinite integral and then evaluate it. And that's how I typically do those, as long as you're careful and don't do any of that poor notation. Questions on that, or questions really about like the poor notation you don't want to show? So there is another way to do it, and you do need to know how to rewrite integrals, because we will get to a point where maybe we don't have to evaluate it completely. We just want to find an equivalent integral where everything is in terms of u. An example where we need to do that, I'm going to use that same example and just like talk about the notation. So we know what an indefinite integral is. When we find an indefinite integral, we just work it out, whether we do u sub or not. All of our answers are going to be an antiderivative plus c. The definite integral, if we are converting this to be in terms of u, we need to make sure we convert every single thing we see in terms of u. And what I mean by that, so focusing on really the definite integral, we said that u was equal to 8 minus 2x squared, like we already did that. We saw that u prime is this negative 4x. So when you rewrote it, we had the integral sign, the x's canceled, so I had that negative 1/4, and then I had the cubed root of u with respect to u. If we want to be truly correct and just be able to rewrite the integral, we want to put those limits of integration, right now they are in terms of x, and we want them to put them in terms of u. And how do we do that? Well, we know what u is in terms of x, this equation right here. So if I have x is equal to 0, that's my lower limit of integration. I can say, well, if x is 0, what is u equal to? Well, u is 8 minus 2x squared. So 8 minus 2, 0 squared, u is equal to 8. So we literally have a correspondence of when x is 0, the u is 8. And then we can do the same thing for 2. When x is 2, what is u? U is 8 minus 2 times 2 squared. 8 times 2 times 4. U happens to be 0. So when x is 2, the u is 0. And this would be considered a correct integral to use. I know it looks weird. You're like, Mr. Brown, those numbers go out of order. It's going from 8 to 0. But you have to remember that we're no longer talking about the x number line. We're talking about this like u number line. So this is everything is now in terms of u. And often the AP exam will add like a multiple choice question, and they'll say, which of the following integrals is equivalent to some given definite integral? And you would have to match it up to that answer. You could actually evaluate it that way. I often don't, but if you evaluate it that way, then you just leave pretty much everything in terms of u. So we have like the negative 1/4 across, the integral of 4/3 times 3/4 again, plugging it in 8 to 0, and you can just leave it all in terms of u. So this becomes negative 3/16 plugging in the top minus plugging in the bottom. So you can also evaluate definite integrals in terms of u. And if you compare them, this answer is literally the same answer you would have gotten if you did it this way. Like this is the 0, and then there's the 8. So you get the same answer, kind of two ways to work it out. So how I wanted to finish up today's notes is going to be the one that says notation du versus dx. I want you to evaluate that definite integral, and I do want you to do it two different ways just to see if you get the same answer and just to kind of practice that method. Option A, I want you to do the indefinite integral first, put it back into terms of x, and then plug in the top number minus the bottom number. For option B, go ahead and practice it where you just put everything in terms of u, including the numbers on the integral sign, evaluate it, and just confirm that you do get the same answer. So go ahead and try those for me. We'll check it, and then this is where we're going to wrap up today's portion of notes. there's my work when you finish to kind of check. Again, that first option, I basically just did the antiderivative first, and then once I found that antiderivative, plugged in the top minus plugging in the bottom. And then the other way is I put everything in terms of u, including the limits of integration. But you see that we do get to the same final answer. And again, mistakes you definitely don't want to make, or you lose points that you really shouldn't lose because you're not like technically doing anything wrong. If you're doing option A, never ever, once you start putting in terms of u, don't put numbers again on the integral sign unless you're converting those x values to also be in terms of u. Again, I will never tell you which way to do it. I tend to just by habit do option A almost every time, but you do need to know how to change limits of integration in terms of other variables as well. But there's my work for both of them, and this is where we're going to kind of wrap up today's meeting. Yeah.
Where does the prime here in the column? Yeah.
So u is 2x, so u prime will be 2.
Yeah.
So this becomes the sine of u, and then dx is du over u prime. So nothing canceled, but like there's still just like a 1/2 on the outside.
So when you have, yeah, I thought you kind of need multiple.
I mean, 1 is a multiple of 2, so it's technically still there.
So we both like this, you just choose the inside.
Right, and this is one integral that many of you could probably do mentally without doing use of. Like I think many of you could say, hey, what's the antiderivative of the sine of 2x? And you know intuitively that's going to be negative 1/2 cosine of 2x. Like that's where that 1/2 is going to get canceled from.
Right.
That's just kind of the use of steps to doing that. But I would expect many of you, especially with practice, like just doing that one mentally, eventually. And save the actual sub process for the more complex ones. I know some of you are still writing that down, but is there anything else I can clarify between those two methods? And then the two definite integrals I have highlighted, those two expressions mean exactly the same thing. One is just in terms of x, the other one is all in terms of u. But you get the same answer no matter which way you do it.